Hi. So on this video, what we're going to do is we're going to look at what's called LeChatelier's principle. The section 5 is called Factors that Affect Chemical Equilibrium. And we'll look at two factors. We'll look at the factor of concentration changes, and then we'll also look at temperature changes as well. Okay, so to begin with, it's not a bad plan to imagine that we have some system that's at equilibrium, right? So let's assume this is at equilibrium. Okay, so what I'm going to do is I'm going to draw a little picture here. So imagine the little circles are the reactant, and the little triangles are products. Okay, 2, 4, 6, 8, 2, 4. Okay, and so let's say that, the reactant is this one, and let's claim that it's reversible to form the product, the little triangle, right? You could use A's and B's, or X's and Y's if you want to do that. Now, let's state for the record that K is equal to the concentration of the little triangles divided by the concentration of the little circles, right? That would be Kc. We could also look at Kp, right? Kp would be the pressure, if these are gases, right, of the little triangles divided by the pressure of the little circles there. Okay. Now I've put in 8 of the circles and 4 of the triangles, right? Since it's at equilibrium, we can figure out what the equilibrium constant is, right? It would be the number of triangles, which is 4, divided by the number of circles, which is 8, which is about 0.5, right? That would be our equilibrium, the value of the equilibrium constant, right? Because we know it's already at equilibrium. Now, what we could do is we could do a little experiment where imagine that we were able to put in, so we're going to add some triangles, right? Some of the product, we're going to add some of them. So I'm going to add, actually, let me make this a different color, just so you can see the ones that I'm adding. 2, 4, 6, 8, just make sure I got everything right there. So I'll make this one blue. So imagine I add some additional triangles. Okay. And you ask yourself the question, are we still at equilibrium? And the answer is no, we're not at equilibrium. What we would do is we would calculate the reaction quotient, right? Remember this from the earlier sections? You would calculate Q. And Q would be the concentration of all of the, it would be the blue ones plus the black ones over the circles, right? Because we've added some extra. So let's see. So I added 4, right? So now what do we have? We have 8 over 8. Hopefully 2, 4, 6, 8. 2, 4, 6, 8. That's 1. So Q is now greater than K, right? It's too high. So that means the reaction is going to shift to the left. And we could go through that arithmetically. What would happen is we would lose some of the products. So we'd have minus X on the product side. So here would be our change. We'd have minus X over here, and then we'd have plus X there. And then it would come to equilibrium, right? Well, maybe we can figure this out. I don't know. I put 4 in there. the ratio really needs to be a half, right, to be equal to K. So if, I don't know, if I took 3 of these blue ones, 1, 2, 3, and converted them into circles, we'd be close, right? Because now we'd have, let's see, I added 1 and I added 3, so maybe 2 and 2. Let's do it that way. But let's leave one of these in here. I could have made up better numbers and made it work out perfectly, but that's okay. Okay, so it looks like we've got 6 of the triangles. And then the number of circles we have was the original 8 plus 1. So is that 9? Let's see, 1, 2, 3, 4, 5, 6, 2, 4, 6, 8, 9. It looks like there's 10. All right, 2, 4, 6, 8, 10. I guess, you know, I'm sorry, I'm counting 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It looks like we have 11 actually. So, you know, that's pretty close to a half, right? It's not exactly half. In order to be a half, it would have to be 6/12. But essentially what we did was we made a prediction, which was that by adding some of those triangles, taking it out of equilibrium, what the system will do is it will promote the reaction in one direction or the other of its choosing to bring the system back to equilibrium. That's LeChatelier's principle, and that's the principle behind factors that affect chemical equilibrium. If you have a system that's initially at equilibrium, right? So step 1, you're at equilibrium. Okay, that's the assumption, we're starting at equilibrium. Now notice that's different than what we looked at earlier in the chapter. Earlier in the chapter, we weren't at equilibrium, then we came to equilibrium. Now we're looking at what happens if we're at equilibrium at the beginning. Step 2, we do what's called a perturbation. Perturbation. That's a U, I'm sorry. Perturbation. We're perturbing the system. So we're changing it so that it is no longer at equilibrium. Okay. So then at step 3, what will happen is the system will adjust and return to equilibrium. Okay, so it's a 3-step process. Start at equilibrium, you perturb the system, it comes back to equilibrium. So really what we need to do is to be able to predict which way it'll go. And in general, it goes the opposite direction of the perturbation. So if you add triangles, the system will turn some of those triangles back into circles to come back to equilibrium. It does the opposite of what you do. So let's take a look at an example. Okay, so using LeChatelier's principle to predict the result of changing concentration. So that's the example we're looking at here. So one point about the equations, the balanced equations here should have the double arrow. Okay. Hydrogen chloride and oxygen react to form water and chlorine like this. 4HCl reacts with O2 to form 2H2O plus 2Cl2. Suppose a mixture of HCl, O2, H2O, and Cl2 has come to equilibrium in a closed reaction vessel. So we can't change the size of the vessel. Nothing can really escape. Predict what change, if any, the perturbations in this table below will cause the composition of the mixture in the vessel. Also decide whether the equilibrium shifts to the left or to the right. Okay, or to the right or the left. Okay, so here we're going to assume we're at equilibrium. Okay, so you have some mixture of all 4 of these substances. Notice these are all gases, so we don't have to worry about heterogeneous equilibria. The reaction can go either direction. So here's our perturbation. We're going to remove some of the H2O. Some H2O is removed. That's a product. So we're going to lower its concentration. So what the system will do is it will accelerate. Really what it'll do is it'll decelerate. It will lower the reverse reaction, right? And then the forward reaction then will take over. Both of those reactions are occurring simultaneously. This is called dynamic equilibrium. So the reactants are turning into products, but the products are turning into reactants. At equilibrium, the rates are constant, so it's not really changing. But if we remove some of the H2O, then the reverse reaction will slow down. If you slow down, imagine like, people are coming out of the train, people are going into the train. If you're at equilibrium, the rates that they're going in and out is equal, and so the number of people stays the same. What we're claiming now is we're going to reduce the reverse reaction. So we're going to make it so that less H2O is going, reacting with Cl2. So the result of that is that the system then, you'll get more of the forward reaction relative to the reverse reaction. So it's kind of cool. So you start building up H2O and Cl2 at the expense of the reactants. They'll go down now, right? So what'll happen is the pressure of HCl will go down. It'll go down because it's going to be used up to replenish that H2O, right? Imagine you've just got like this tank here, these two tanks that are the reactants, and they're connected to form the products. If you take some of the product off, and the system is trying to keep the products constant, some of the reactants will react to make more of the products, so you start losing reactants. So HCl will go down. So will O2, right? So both of these are on the same side. So if one of them goes down, the other one's got to go down too. So these will both decrease, and the equilibrium will shift. Well, you shift to the right. You shift to the side that you removed the product from, okay? So you take H2O. Okay, so we're at equilibrium, step 1. Step 2, you take away H2O. That's called the perturbation. Step 3, the system will replenish the H2O. Maybe not all of it, but some of it, by reacting the two reactants. So the reactants will decrease in pressure and the products will increase in pressure. So it doesn't really ask us about the products here, it just asks us about the reactants. The equilibrium is shifting to the right. The right is the product side. We're replenishing the H2O, and you're going to produce more Cl2 also. Okay. Some O2 is added. Okay, so now here's some O2. We're going to add some of this, right? Okay. Adding O2 is going to accelerate the reaction rate in the forward direction, right? Remember, rate is equal to K times the concentration or pressure of the reactants multiplied together. So if I add more O2, that's going to make the reaction go faster in the forward direction. Okay. The result of that is you'll start building up more H2O and you'll start building up more Cl2. So HCl and H2O, well, here's HCl. That's going to go down. That pressure is going to decrease because it's going to be used to make these products. H2O, be careful. This is on the other side. This is going to increase. The pressure of that will increase as you start producing it. So again, the reaction is shifting to the right. So notice in the first one, you removed water. That causes the reaction to shift to the right. You added more O2 in the second one, and that also caused the reaction to the shift to the right. But that's essentially what happens. There's two ways to shift a reaction to the right. You remove some of the product or you add more reactant. Okay, let's take a look at another one. Same idea. You got two reactants, two products. Everything's a gas phase. We're at equilibrium. We add some O2. So we add O2. That's going to accelerate the forward reaction. So you're going to start losing H2S, losing O2 as they get turned into SO2 and water. You'll get more SO2 and more water. So the pressure of H2S will decrease. The pressure of SO2 will increase. Okay, shifting to the right, right? If the product's increasing, that's shifting to the right. Remove some H2O, taking away this product. The reverse reaction will now slow down and you'll have, it will no longer be at equilibrium, right? The forward reaction will now be faster than the reverse reaction. So you're going to, again, you're going to shift to the right. You're going to start producing more SO2. So H2S will decrease and O2 will also decrease as you replenish the SO2 and the H2O for it to return back to equilibrium. Again, you're going to shift to the right. Okay. So that's called LeChatelier's principle. And it's essentially, just to put it in a bit of an equation, if you have A plus B, and again, it is reversible, C plus D. If you were to eliminate D, the reverse reaction would go down to 0, right? You would have no reverse reaction because you don't have a product to do the reverse reaction. So that means you're only going to have a forward reaction. So the pressure of C will start going up. The pressure of D will start going up. The pressure of A will start going down. And the pressure of B will start going down. And we would call that shift to the right. Okay. On the other hand, imagine that we removed one of the reactants. Okay. Well, now, since we don't have this reactant, the only reaction that's going to happen is the reverse. Only the reverse reaction will occur. Okay. So that means this forward reaction isn't even occurring. So the reaction is going to shift to the left. Okay. Now, you don't have to eliminate it completely. Even if you reduce the concentration by some amount, that will upset the balance of the two reaction rates. Remember, the reaction rate is forward and reverse. Okay. So if I eliminate A, the only reaction that can occur is the reverse reaction. So it's going to shift to the left. So these pressures will decrease on the product side as they react. And then these reactants will increase. Now, you could take all of the A out, but you'll still get A back because it's coming from this reaction here. Okay. Let's take a look at one more type of problem. There's typically 3, but we're just going to look at 2 in this course. The second one we're going to look at is the effect of temperature, which is not an obvious relationship. Okay, so let me bring this up. Okay, so we're going to use LeChatelier's principle. So using LeChatelier's principle to predict the result of changing temperature. Okay, remember, LeChatelier's principle says that if you perturb a system that is originally at equilibrium, the system will respond to that perturbation by returning to equilibrium. Okay. Nitrogen and oxygen react to form nitrogen monoxide like this. N2 plus O2 forms 2NO. Again, it should be a double arrow. The reaction is endothermic. Suppose a mixture of N2, O2, and NO has come to equilibrium in a closed reaction vessel. Predict what change, if any, the perturbations in the table will cause in the composition of the mixture in the vessel. Also decide whether the equilibrium shifts to the right or the left. Okay. Now, this is the effect of temperature. So in order to answer this question, I want to go over a little bit about temperature. There we go. The issue here is that in some of these problems, if you have a reaction, and again, I'm just going to make it a nice simple reaction. When we say that something is endothermic, that means it absorbs heat. This is called endothermic. So it absorbs heat, right, from the surrounding. Remember, you have these symbols. Q is heat, but at constant pressure, the heat is equal to the change in enthalpy, delta H. If it's endothermic, what we do is we recognize it as being a requirement for the forward reaction. So we put delta H on the reactant side, and we treat it for the purpose of these types of problems as an actual species in the reaction. It's a requirement for the reaction. If there is no heat, if there's no enthalpy change, then there's no reaction, essentially. Then we point out that heat and temperature are related to each other, right? So if you add heat, the temperature rises. So temperature increases with additional heat. So whenever you add heat, you increase the temperature, right? Or if you increase the temperature, you're adding heat, right? So if you want water to get hotter, what do? You add heat, right? So heat and temperature are related, but so we're talking about heat. Here's our enthalpy. If it's endothermic, we're going to put it on as a reactant side, on the reactant side as a reactant. If it's exothermic, that means it produces heat. So we're going to put it over here. We're going to call that exothermic. Okay, releases heat. Heat is not really a thing. It's a relationship between particles, but we can often think of it as being a useful way of thinking of it as like being released or absorbed. Okay, really it's energy that's being absorbed or released. Okay, so in the example that we have here, it's endothermic. So then once you know whether it's endothermic or exothermic, you can put it on the side that you need to put it on, and then just treat it as if it were a reactant or a product, depending on the example. Just like we did in the previous example, if you increase the pressure of a reactant or you decrease the pressure of a product, right? You remove some or you add some. You can do the same thing with the heat. It's a clever way of thinking about it, okay? So in the example that we have for this one, okay, let's put it up here. We have N2 and O2, and that forms 2NO, okay? It says it's endothermic, so we're going to put delta H on the reactant side and treat it like a reactant. So if you lower the temperature, temperature's going down, decreasing, the heat is going down, because remember, temperature and heat are related to each other. They're proportional, essentially. The change in temperature is proportional. So if you lower the temperature, you're removing some of the heat. And that would be like removing some of the reactant, right? Because if it's endothermic, it's on this side. So if you remove some of the reactant, just like our previous examples, that's going to slow down the forward reaction. So the reverse reaction will now be dominant. And so you'll start forming more reactant. It'll shift to the left. So if we lower the temperature, it'll shift to the left, and the pressure of NO should decrease, right? The products will start getting converted into reactants. So it's not obvious. You would think, oh, I'm going to cool the reaction down. That actually has the result of shifting the equilibrium to the left and reducing the pressure of NO and increasing the pressure of N2 and O2. This is actually a clever way that we can do that. If you can use temperature changes to shift the reaction one direction or the other, okay? Let's take a look at another example. The temperature is raised. So again, it's endothermic. You have to look for whether it's endo or exo. It's endothermic, so it's up here. So if you raise the temperature, that's like increasing the pressure of a reactant. So it's going to shift the equilibrium the other direction, right? It's going to make the forward reaction become dominant. So now NO will start increasing in pressure. N2 and O2 will start decreasing in pressure. It's shifting it to the right, and pressure of O2 will be decreased. Okay, let's take a look at another example. This one, similar one, you've got two reactants in one product. This one, however, says it's exothermic, okay? And so for this one, I'll go ahead and write out the equation here on the whiteboard. And again, they say it's exothermic, so you put your delta H on the product side. Okay, put it on the product side there. You should be in good shape. In this example, they say that the temperature goes down. So it goes down, right? So that's like lowering the delta H. Has the effect of reducing the amount of heat that's released, okay? So again, remember, you think of this, you've got two competing reactions. You got a forward reaction and a reverse. If you decrease the amount of the reverse reaction, pressure or heat in this case, then this is going to go slower, right? Because remember, your rate forward is equal to K forward times, concentration of N2, concentration of H2 to some power. We don't know what they are. Presumably they're not 0. But then you get the reverse reaction, which is K reverse times the concentration of NH3. And you can use pressures if you want, and we don't know what that is either, okay? But we now also have our delta H in here. Okay, I'm kind of pushing here the analogy, because remember, heat is not a reactant, it's not a product, it's a relationship of energy. So we're pushing our analogy a little bit here, but I just want you to kind of get the idea, is that if you're at equilibrium, these rates are equal. This forward and reverse reaction rates are equal. They're going at the same speed. So that's why it's at equilibrium. But if I lower the amount of heat, then that's going to make this go slower. So if this one doesn't change, but this one does, overall, the forward is now going to be larger than the reverse, right? R for reverse. Sorry, I'm using an uppercase there. I should stay consistent with the lowercase. Reverse, right? R-E-V-F-O-R. Okay, right? Like if you have two competing phenomena that are at the same rate, and then you slow down one of them, now the other one is going to be going faster, right? Like two cars, they're racing, they're going the same speed. If one slows down, now this one's going faster. So what happens then is, since the reverse reaction is going slower, the forward reaction will now take over, okay? If it takes over, this is going to start increasing. This is going to start decreasing. This is going to start decreasing. So the pressures of the reactants will go down and the pressure of the product will go up. That's essentially the idea. So it says, as the temperature is lower, the pressure of NH3 should go up as the reaction shifts to the right. So this is actually a way, if this reaction is exothermic, this is a way to actually get more product. You can make more ammonia, even if the equilibrium constant is small, by just cooling it down. Cooling it down will cause the reaction to go forward. And that's the way to make more ammonia, NH3. Okay, shifts to the right. Now, in the second part, they say the temperature goes up. Okay, so I'll bring that up here. So in the second part, it says the temperature goes up, right? Remember, it's exothermic, so delta H is over here on the right side. So if it goes up, you're now, again, you're accelerating the reverse reaction, right? You're accelerating the reverse reaction because you're making one of the products increase. So that means the reverse reaction is going to take over. N2 is going to increase, H2 is going to increase, and NH3 will decrease. So raising the temperature will actually cause the equilibrium to shift to the left. So that goes to the left, and H2 will increase in terms of its pressure. Okay, so there is actually a third type, which I didn't assign for you, about, if you have gases and you compress them or you expand them, about pressure. But I didn't want to put that in there because, there wasn't a particularly good problem on Alex with it. But essentially what happens is, if you have an equation of gases and you increase the pressure of that mixture of gases, that will shift the equilibrium toward the side of the equation that has fewer gas molecules, fewer gas molecules. If you decrease the pressure, so if you expand the gases, that will shift the equilibrium towards the side of the balanced equation that has more gas molecules, okay? And that's our third relationship. So there are three. There's concentration changes, there's temperature changes, and then there's pressure changes, okay? So that is LeChatelier's principle, and that ends the last section that we're going to cover for chapter 15. So take care.